All right, let's dive right in. We're going to talk about the incredible, almost magical world of AI video. Now, we've all seen the jaw dropping clips, but today we're going to look past the illusion and ask a really important question. Can you actually play in these AI generated worlds?
So, you've seen it, right? Models like Sora can take just a few words, a simple text prompt, and create videos that look so real. It honestly feels like magic, like we finally cracked it. Like we taught a computer to understand our world just by showing it a ton of YouTube videos. And visually, wow, it's an amazing trick.
But, and this is a big but, here's where that magic starts to get a little bit fuzzy. What happens when you want to do more than just watch? What if you want to, say, pick something up or open a door? What happens if you knock that glass off the table? All of a sudden, that beautiful, perfect illusion, it shatters. Turns out you can't really play inside a painting, no matter how photorealistic it looks.
And that really gets to the heart of the problem. You see, current AI video models, they're amazing at creating the ultimate passive experience, a movie. But a true world model, well, that needs to be more like a game. It has to get causality, cause and effect, the idea that every single action you take has a logical, consistent consequence. And believe me, that is a whole different ballgame than just predicting the next pretty pixel.
This brings us to a really deep, almost philosophical debate in the world of AI. For a long time, the main idea has been just get bigger, right? If you just show an AI enough videos, if you just scale it up, it'll eventually figure out physics, logic, everything. But a new philosophy is emerging that says, nope, without an underlying structure, all you're doing is building a smarter parrot, not an AI that truly understands. It's about structure, not just scale.
So how do you build that structure? Well, the answer might just be the one thing that makes us, human, language. The philosopher Dan Dennett has this great way of putting it. Language is a cognitive tool. It lets us create abstract symbols for really complex stuff, things like gravity or friendship or even the rules of chess. This is what lets us reason about the world in a way that just looking at pixels never ever could. And this table just lays it out perfectly. It shows the two competing teams. On one side, you've got the pixel-first approach. Think of this as a brilliant painter, totally focused on creating a beautiful, but ultimately static image. On the other side, you have the structure-first approach, which is being pioneered by a company called Moonlake. They're acting more like a physicist and an architect combined. First, they figure out the rules, the logic, the physics of the world. And only then, after all that's done, do they worry about how to paint it.
So how does this whole structure-first thing actually work in practice? Well, Moonlake's method is basically a two-step process that completely flips the usual way of doing things on its head. It's all about thinking before you paint.
Let's make this real. Imagine you give the AI a prompt. Create a bowling game. Okay, a pixel-first model might spit out a really convincing video of a bowling alley, maybe someone throwing a strike. But a structure-first model has to do something way deeper. It actually has to understand what a game is and then build it from the ground up. This is what Moonlight calls a reasoning trace. Let's break it down. First, the AI understands the abstract rules. What's a pin? What's a ball? How does scoring work? Then it reasons with physics and logic. A heavy ball hits wooden pins, which causes them to fall over. Simple, right? Third, it constructs the world state. That's the exact position of every pin, the score, whose turn it is. And only after all that logical work is done does it actually render the visuals you see. Okay, so the first piece of their system is this multimodal reasoning model. Now, multimodal just means it understands different kinds of information all at once. Text, images, logic, you name it. Think of this part as the brain of the whole operation. It's not a graphics card, it's a logic engine. It gets the abstract, symbolic representation of the world. It's the architect drawing up the blueprints for our bowling alley. And the second part is an image generator called a diffusion model, which they've named Ray. Now, if the reasoning model is the architect, Ray is the brilliant interior designer and the master painter. It takes that logical skeleton, the blueprints, and drapes this gorgeous photorealistic skin over it. But here's the crucial part. This visual layer has to respect the underlying logic. It makes things look pretty, but it can't break the rules of the world. Okay, so this is a really clever technical solution. But so what? Why does this matter? Why go through all this trouble instead of just making bigger and bigger video models? Well, the answer is that it unlocks entirely new categories of things that AI can create. This is about more than just better-looking videos. Because you have that structural foundation, you can build truly interactive games, not just videos that look like games. You can create what they call programmable renderers. Imagine applying a cyberpunk skin to your entire world, and the core logic stays exactly the same. How cool is that? You can build amazing training grounds for robots and AIs because they can finally learn from real cause and effect. And you get long-term consistency. The world actually remembers its state. It doesn't just remember what the last video frame looked like. And here is the absolute kicker. Because this whole approach is working with abstract, symbolic data instead of giant, messy pixel data, it can be unbelievably more efficient. We're talking potentially 5 orders of magnitude less data. That's 100,000 times more efficient. That completely changes the game for training these enormous models. Now, this all sounds incredible, right? But it also creates a brand new challenge. If we're not just making pretty videos anymore, how on earth do we measure if we're doing a good job? This takes us to the next frontier. How do you actually benchmark a world? Seriously, think about it. It's a really hard question. For a picture, you can measure how realistic the pixels are. For a language model, you can quiz it on facts. But how do you grade a reality? How do you score an experience that's supposed to be fun and interactive and consistent? All our old benchmarks just don't cut it. Yeah, measuring pixel fidelity, that's the easy part. It gets way harder to design a test for something like logical consistency. But the real test, the ultimate metric, is just, do people want to be there? Can a game designer take this tool and build something amazing? Do people actually want to spend time in this world? The best world model is probably the one that people actually choose to live in.
And that really leaves us with this one big final thought. This whole debate between pixels first and structure first, it's not just a technical argument between engineers. It's a question about what our ultimate goal is with artificial intelligence. Are we just trying to build better, more convincing movies? Or are we trying to build entirely new, interactive, and programmable realities? The answer to that question is going to define the next decade of AI.